Hello and welcome to Joey's AP Precalculus. Today we will be going over lesson 1.7, rational functions and end behavior. We have one lesson objective today, describe end behaviors of rational functions. So first of all, let's learn what a rational function is. A rational function is the quotient of two polynomial functions, f of x and g of x, where g of x is non-zero. So essentially, we can represent a rational function as a quotient of two polynomial functions. So it's essentially a fraction where the denominator and the numerator are polynomial functions. But you have to make sure that the polynomial function in the denominator is not zero. So rational functions give a measure of the relative size of the polynomial function in the numerator compared to the polynomial function in the denominator. I'll explain in detail what that means. So let's look into what end behaviors rational functions have. So the end behavior of a rational function is the same as the end behavior of a rational function's quotient of the leading terms in both the denominator and the numerator. This may be complicated, so I'll be showing you different examples and demonstrate how end behaviors might differ in different situations. So if the numerator of the rational function has a greater degree than the denominator, meaning that in this example, if you take a look at the numerator has a degree of 2. However, the denominator has a degree of 1. In this case, the quotient of the leading terms would be a non-constant polynomial, and the end behavior of a rational function would follow that non-constant polynomial. So in like this example where the denominator has a smaller degree than the numerator, or in other words, when the numerator has a greater degree than the numerator, you can simply just take the two leading terms and divide them. If you were to divide them, you'll be getting 2x over 3. So you can essentially conclude that the graph above follows the same behavior as y equals 2x over 3. Y equals 2x over 3 essentially has an end behavior of as x goes into positive infinity, y goes to positive infinity, and as x goes to negative infinity, y goes to negative infinity. So that's essentially the end behavior of this rational function. If the denominator of a rational function has a greater degree than the numerator, the quotient of the leading terms would be a rational function, and the horizontal asymptote would be at y equals 0. So whenever the denominator has a greater degree, just like the example we have here, there will be a horizontal asymptote at y equals 0. And the end behavior will be always something like as x approaches infinity, y approaches 0. And as x approaches negative infinity, y approaches 0. So that's essentially the case when the denominator has a greater degree than the numerator. Our last scenario is when the denominator and the numerator has the same degree. In that case, the quotient of the leading terms would be a constant. Why? Right? Because if we take the two leading terms and if we divide them, we would be simply getting a constant like this. In that scenario, that constant is the horizontal asymptote of the rational function. As you can see from this example, the graph above has a horizontal asymptote at y equals 2 because the leading term's degree in both the denominator and the numerator are the same. In that case, we can represent the end behavior as x approaches infinity, y approaches 2, and as x approaches negative infinity, y approaches 2. Now let's go over horizontal and oblique asymptotes of rational functions. So a rational function has a horizontal asymptote when the denominator and the numerator have the same degree or when the denominator has a greater degree. As I explained in the previous concept, the horizontal asymptote is y equals 0 when the denominator has a greater degree than the numerator. Horizontal asymptote is a divided by b when the numerator and the denominator have the same degree. That's a scenario that we looked with this example, right? When the denominator and the numerator have the same degree, this assumes that a and b are the leading coefficients of the numerator and the denominator respectively, and we can conclude that the horizontal asymptote is simply a divided by b. A rational function has an oblique asymptote when the degree of the numerator is exactly one more than the degree of the denominator. This is kind of like the scenario that we looked over here. Because if you take a look at this, the numerator has a degree that's exactly one more than the denominator. In those scenarios, the end behavior always follow the quotient of the leading terms. But other than the end behavior, there's also something called oblique asymptote. Oblique asymptote is a linear function which has a slanted shape. So oblique asymptote is the quotient when dividing the numerator and the denominator, and the remainder can be disregarded. What this means is that if we divide x squared and x plus 1, yeah, my bad. We'll be getting the quotient of x minus 1 and the remainder of 1. But we can disregard the remainder, and whatever we get as the quotient is our slanted asymptote or oblique asymptote. So whenever the denominator is 1 degree less than the numerator, or in other words, whenever the numerator is 1 more than the degree of the denominator, we always have an oblique asymptote. And how can we find that oblique asymptote line? We can simply divide the denominator and numerator, and whatever we get as the quotient is our slant asymptote or the oblique asymptote. Yeah, so the graph never touches this oblique asymptote, but it does approach it from both sides. But still, if you can look at the overall end behavior, the end behavior is essentially the behavior of a graph when the graph approaches positive infinity and the negative infinity, right? If you take a look at the end behavior, it's still the shape of y equals x. The reason why is because, as I told you, whenever the numerator is greater than the denominator, the degree of the numerator is greater than the denominator, the end behavior is same as the quotient that we get by dividing the two. So essentially, when we divide the leading term of the numerator and the leading term of the denominator, we get y equals x. That's why the overall end behavior of this rational function is the same as the end behavior of y equals x. Great. Now let's learn about end behavior and horizontal asymptotes for rational functions. So when a rational function has a horizontal asymptote at y equals b, the end behavior of the rational function written in limit notation is limit of f of x as x approaches infinity is b, and the limit of f of x as x approaches negative infinity is b. So as I just told you, whenever we have a horizontal asymptote, it means that whenever the graph is approaching positive or negative infinity, the graph is approaching that horizontal asymptote line. It never touches that line, but it is approaching. If you take a look at this example, because the degree of the denominator and numerator are the same, we can simply conclude that this rational function would have a horizontal asymptote at y equals 4x squared over 2x squared, or that's simply 2. That is true because, as you can see from this example, this rational function indeed has a horizontal asymptote at y equals 2. In that case, we can express that its end behavior is as x approaches infinity, y approaches 2, and as x approaches negative infinity, y approaches 2. We can also write this in limit notation, as we learned in our previous units, as this. This is essentially the same as x approaches infinity, y approaches b, and this is exactly the same thing as x approaches negative infinity, y approaches b. So whenever we have a horizontal asymptote, note that the end behavior will involve that horizontal asymptote line. Now let's try some examples that are kind of similar to AP style questions. So if you take a look at example 1, the rational function g is given by g of x is equal to x to the power of a times x squared plus 1 times x minus 1 over x to the power of 8 times x squared minus 2, where 8 is a whole number. What is the value of a if g of x has a horizontal asymptote of y equals 0? So let's kind of give us a reminder of how horizontal asymptotes might differ. When are instances where the horizontal asymptote is y equals 0? So the horizontal asymptote of y equals 0 happens when the denominator's degree is greater than the numerator's degree, right? As you can see from here, when the denominator has a greater degree than the numerator, then there is a horizontal asymptote at y equals 0. So essentially, our mission is to find the a value so that the denominator's degree is greater than the numerator's degree, and it's all good. So first of all, let's try to expand this, okay? Let's try to expand the denominator first. If we were to use the distributive property, we can get x to the power of 10 minus 2x to the power of 8. For the numerator, let's first expand this using the FOIL method. We'll be getting x cubed minus minus x squared plus x minus 1. So we'll be having x to the power of a times x to the power of 3 minus x to the power of 2 plus x minus 1. So great. Whenever we're dealing with like horizontal asymptote or end behavior problems, we're only looking at the leading term of both the denominator and the numerator, right? So we have a leading term of x to the power of 10, and our leading term of the our leading term of the numerator would be the result that we get from multiplying x cubed and x to the power of a. So essentially, our task is that x to the power of a times x to the power of 3 is less or smaller than x to the power of 10. Then what is the value of a if g of x has a horizontal asymptote of y equals 0? The answer is that a should be less or equal to 9. And you have to mention that yeah, I think that's it. Yeah, and let's mention that a is a whole number. Yeah. This is the correct answer because under the condition, sorry, a should not be less than 9. That is my bad. That is incorrect. A should be less than 6. Yeah, because if you were to set a as 6, x to the power of 6 times x to the power of 3 would be x to the power of 9, which is less than x to the power of 10. So that is a correct answer. So your answer for this question should be a is less or equal to 0. Sorry, a is less than or equal to 6, and a is a whole number. That is an absolutely correct answer. And yeah. Let's also look into question number 2. Describe the end behavior of the function f of x is equal to x squared minus 4 over 5x squared minus 5. Use limit notation. Support your answer by comparing the degrees of the denominator and the numerator of f of x. So in this case, because the degree of the denominator and the numerator are the same, we have a horizontal asymptote at when the horizontal asymptote is essentially the quotient of the two leading terms we have. So it's essentially y is equal to x squared over 5x squared. That is essentially 1 over 5. So essentially, that's it. We found that the horizontal asymptote is 1 over 5, and we can use a limit notation to describe the end behavior. You can say that the limit as x approaches infinity of f of x is 1 over 5, and that the limit of f of x as x approaches negative infinity is also 1 over 5. That is an absolutely correct answer using the limit notation. And we also supported the answer by comparing the degrees of the denominator and the numerator. We can also add that the degree of the denominator and the numerator are the same. Great. Let's look at example 3. Rewrite the following function in a single fraction using the least common denominator and describe its end behavior. Use limit notation. So essentially, we have to write this in a single fraction. How can we write this in a single fraction? If we were to write this in a single fraction, these two fractions needs to have the same denominator, and we have to find the least common denominator. The simple method of doing that is by multiplying the denominator of the second fraction to the first fraction. So we're going to multiply x minus 4 in both the denominator and the numerator so that it is valid in the first fraction we have. And in the second fraction, we're going to do the same thing. But in this case, we're going to multiply x minus 2. So if we do that, we will be having the same denominator. And then we can now combine the numerator because the denominator would be the same. So if we were to use a distributive property to expand out, we'll be getting 3x squared minus 12x. And if we were to expand that using the distributive property, we will be getting 4x minus 8. So if we were to kind of simplify this, we will be getting 3x squared minus 8x minus 8 over, if we use a full method, x squared minus 2x minus 4x plus 8. That can be written as x squared minus 6x plus 8. And that is what we have. We have written this two different fractions into a single fraction like this. We can also describe its end behavior because the degree of the denominator and the numerator are the same. We can know that they have a horizontal asymptote at y equals 3. Because if we divide 3x squared and x squared, we get 3 as our quotient. So we can write the end behavior of this as the limit as x approaches, the limit of f of x as x approaches infinity is 3, and that the limit as x approaches negative infinity of f of x is also 3. So our two answers would be this end behavior written in limit notation, as well as this expression here written in a single fraction. Great, let's look at example 4. Determine any horizontal or oblique asymptotes and intercepts. Support your answer by comparing the degrees of the denominator and the numerator. Okay, so first of all, we can find that the oblique asymptote that we have here, right? Why does this have an oblique asymptote? The reason why is because the numerator has a greater degree than the numerator, and the difference between the denominator's degree and the numerator's degree is exactly 1. So we can conclude that this does have an oblique asymptote. How can we find out? We can do that by dividing the numerator and the denominator like this. we can use a long division method. So if we were to divide them, we will be getting x squared plus 4x. Let's subtract them. Minus 1 minus x minus 4. Great, so we already found the oblique asymptote. We can conclude that the oblique asymptote occurs at y is equal to x minus 1. Great, let's determine if this also would have some intercepts. Okay, how can we find if this has an intercept? So y-intercept, the definition of y-intercept is y value when x is equal to 0. So if we were to plug in 0 to this entire thing, we will be getting y is equal to minus 4 over 4, or minus 1. So we essentially found out the y-intercept is at 0, negative 1. Great. Let's also see if there are any x-intercepts. X-intercepts occur the definition of x-intercept is the x value when y is equal to 0. So let's determine the x value when y is equal to 0. So it's essentially 0 is equal to this, right? Okay. Great. Okay. If we were to kind of factor our polynomial expression in our numerator, we can get xx 4 minus 1. And if we kind of do cross multiplication, we can get 4x and minus x, which does give us 3x. And if we multiply them, we will be getting minus 4. So essentially, we can rewrite the numerator as x plus 4 and x minus 1. So essentially, our x-intercept can be x equals minus 4 and x equals 1, because if we were to plug this into here, that would make the numerator 0, and therefore the entire fraction 0. However, x equals minus 4 cannot be an x-intercept. The reason why is because there is, because that at x equals negative 4, the entire fraction or the entire function would be undefined. The reason why is because we have x plus 4 in the denominator as well. So if you were to plug in x is equal to negative 4, that would make the numerator 0, but also the denominator 0. In that case, the entire fraction would be undefined, so that is not a valid x-intercept. However, x is equal to 1 is a valid x-intercept. So we can conclude that x-intercept is at 1, 0. That's correct. We have an oblique asymptote at y is equal to x minus 1, and we found two intercepts, one y-intercept at 0, negative 1, and one x-intercept at 1, 0. That is completely correct, and you can also you can perhaps add an explanation that we can find the oblique asymptote because the degree of the denominator and the numerator are this. Because the degree of the numerator is exactly 1 more than the degree of the denominator. That's also a good kind of like an additional info to add. Yeah, but I think other than that, we touched upon every single example existing in this lesson, and hope you nailed this concept of end behavior and horizontal asymptotes, as well as oblique asymptotes. Thank you so much for watching, and make sure to email me or comment in the video section if you have any questions. Thank you so much for watching.